In this video, we're going to take a look at section 8.1 on the basics of hypothesis testing. In statistics, a hypothesis is a claim or statement about a property of a population. So for example, we might say that our hypothesis is that the mean of the age of students in statistics is 20. And that could be our hypothesis. Right? Now, in order to determine whether that hypothesis seems to be true or not, we use what's called a hypothesis. I want to say an hypothesis, but that doesn't sound right either. A hypothesis test, which is a standard procedure for testing a claim about a property of a population. So in this chapter and in the next chapter, we are going to be making claims about populations, either about proportions regarding that population or about means regarding that population. And then we're going to be able to test that claim using a sample and a hypothesis testing process that we are going to go over today. Now, this process has multiple parts to it. It's a very, complex process. And so we have to talk about each part individually, how to carry out that particular step of the process, and then how it all kind of ties in together. So this section, we're just going to consider each step individually. And then once we have done that in this section, then in the next section, we'll do problems where we just kind of go through the process in its entirety. So it'll seem a little bit fragmented in this video as we look at the steps separately, but then in the next section, hopefully we tie it all together. You can see how all the pieces of the puzzle fit together to provide a conclusion about a claim that's being made regarding the population. All right, so here are all the steps to hypothesis testing. First, we will identify the claim. So the problems that will be given will paint a picture for us, provide some information, and then give us a claim, but the claim is written verbally. So it's written out in words. We want to take the claim and translate it into the language of math. So we want to take the claim and write it in symbolic form. So we have to find the claim in the problem that we're given and then write that claim mathematically. Then we take the claim and convert it into what are called the null and alternative hypotheses. So this is the way I kind of think of the hypothesis testing process. It's like a machine. And so think about like a factory or something. And if you want the machine to produce something for you, you have to give it resources, but the resources that you provide it have to be provided in the right way for the machine to work. Trying to think of some like other non-statistics example of that, but like, I don't know, I'm trying to think of some kind of a machine, like a machine that makes pencils, for example, right? Pencils are made out of wood, at least traditionally they used to be. But you can't just give the machine a tree, right? That wood has to be processed a certain way first before you feed it into the machine that makes pencils. That's what we're doing here, right? In order for hypothesis testing to work, we have to format the claim in the right way to feed it into the machine so that it can crunch the situation. Maybe crunch the situation sounds a little weird, but it's going to take the information we provide it, run some tests on it, and then produce an output for us, which is the conclusion. All right, excuse me. All right, so I hope that, I don't know, I felt like I hit on something pretty good there, and then I just kind of botched it at the end the way I described it. But okay, so we set up what are called the null and the alternative hypothesis so that the hypothesis testing process can be applied to that. Identify alpha, which will be given to you in the problem, and this isn't really hidden information. They're going to, it's just given to you directly. Now, we talked about alpha in chapter 7, and in chapter 7, alpha was 1 minus the confidence level for our confidence intervals. It wasn't really given a name. My recollection is I don't think there was a name given to it, but we do have a name for it in this chapter, and it's called the significance level. And maybe that's the proper name for it in chapter 7 as well. I'm not sure. But that's what you want to look for in the problem. It'll say the significance level is 0.05. that means alpha is 0.05. So identify that value of alpha and determine whether the test that you're about to do will be a left tail, right tail, or a two-tail test. All right. And we'll talk about how to do that later in the video. Then, and this isn't really like sequential, so that third step could be done later, but I just go ahead and throw it in there now. I don't know. So that's kind of flexible. The next step is to calculate the test statistic, which again doesn't rely on alpha. It doesn't rely on whether it's a left tail, right tail, or two-tail test. So that prior step doesn't really feed into the calculating this test statistic step. But what does feed into that is the null hypothesis. So we will need the null hypothesis in order to calculate the test statistic, in addition to our sample data. And so here's where we kind of merge the two pieces of the puzzle together, right? We have the claim that's being made, which was formatted into a null hypothesis and an alternative hypothesis. That null hypothesis feeds into this formula called the test statistic, and so does our sample. So our claim and our sample data kind of converge with the test statistic calculation. Right? So there will be a formula for that, and we'll talk about what the formula is. It's different whether you're testing a claim about a proportion or about a mean. So there's two different formulas for the test statistic depending on what your claim is about. Then determine the critical value and or the p-value. Now many of these problems will ask you to do both. You'll be calculating the critical value and the p-value, but in reality you only need one of these to move on to the next step. Now the critical value is going to be based on alpha. The p-value is based on the test statistic. So you can't find the p-value until you have the test statistic. All right, those numbers are comparables. I don't know a good way to describe it. So when you calculate the test statistic, you're going to get a value, and that value is based on the null hypothesis, which we're assuming to be true without any evidence. We're just going to take the null hypothesis and, for the sake of argument, assume that it's a true statement. And then we're, including the sample data with that assumption in calculating the test statistic. And what can happen is the sample data we have might come out as an ordinary looking sample where our test statistic is a reasonable number, in which case the assumption we're making, the null hypothesis, seems to be fine. It seems to be like it doesn't seem out of the ordinary. The other thing that can happen is when you calculate the test statistic, you get this really extreme value for the test statistic. And in that case, it makes the assumption look questionable, right? Where do we draw the line between what is an ordinary test statistic and what is an extreme test statistic? That's what the critical value is for. The critical value tells you that threshold, that this is the line we draw. Before it, the test statistic, if the test statistic is before that critical value, it's ordinary. Nothing out of the ordinary here. If it's past that critical value, that's extreme and there's something wrong. And the thing that's wrong is the null hypothesis, right? That's something we assumed without evidence. And if something looks wrong, it means that assumption was probably bad, right? So that's what the critical value is for. The p-value makes the same kind of comparison, but from a different angle. And so the p-value, what you do is you take your test statistic and convert it to an area. So alpha is an area, right? If remember from chapter 7, we take alpha, we divide it by 2, we make it the area in the left and right tail. So alpha is an area. And for critical value, what you're doing is you're taking your area of alpha, converting it to a t-score or a z-score, depending on the circumstances, and comparing that to the test statistic to draw your conclusion. For the p-value, what you're doing is taking the test statistic and converting it to an area, and then you compare that area to alpha. So again, it's really trying to compare the same two things, but either you're comparing z-scores or you're comparing areas with one another. What's nice about the p-value is the rule for drawing your conclusions pretty straightforward once you have the p-value. It's a little bit harder to analyze with the critical value. Critical value is the more traditional way. In fact, that's, I think, what the textbook calls it. Using the critical value is the traditional method. The p-value method's a more recent concept that has been adopted for its simplicity, because once you have the p-value, the rule's pretty simple from there to figure it out. So you take the test statistic, convert it to an area. There's some rules about how to do that, but that area then gets compared to alpha, and then based on that comparison, you draw your conclusion. And it's the same idea. It's a threshold thing. So alpha becomes your threshold there. And if the p-value is smaller than alpha, you do one thing. If the p-value is bigger than alpha, you do a different thing. All right. And that thing you do is draw the initial conclusion. So the next step, once you have your critical value or your p-value, you make the proper comparison and then draw your initial conclusion, which will be one of two things. Either you reject the null hypothesis, meaning you reject the assumption that we made that the null hypothesis was true, right? So if things look really extreme, the assumption looks like a bad assumption, that means we're rejecting the null hypothesis because our assumption was the null hypothesis. If we think it's a bad assumption, it's a bad null hypothesis. So we reject it. We say that doesn't appear to be true. It seems to be false. Or we fail to reject the null hypothesis, which is to say that we mean we couldn't show it was false. Now, a lot of students assume if you have a statement, it's either true or false, right? So if we're saying reject the null hypothesis means the null hypothesis is false, then the other option would be to say that it's true, right? Because either it's true or false. So if we determine it's false, that's one thing, but if we don't determine it's false, then it must be true, right? But that's not the case either. So the initial conclusion we're drawing is to either say the null hypothesis is false, reject the null hypothesis, or we were unable to show that it was false, but we're not necessarily asserting that it's true either. We're just saying the data just wasn't strong enough evidence to prove this was false. But we don't want to go as far as to say that means it's definitely true. And the exercise I like to do in class sometimes, now I don't always do this, but if a student asks like that doesn't make sense. It's either true or false. I do this exercise, which is I'm going to think of an animal. And I want you to guess the animal I'm thinking of, right? So I'm thinking of an animal. I want you to guess the animal that I'm thinking of. And then I'm going to give you a clue. And then based on that clue, I want you to tell me, what you think. So I'll give you the clue and then we'll consider what that clue tells you about your guess, right? So my clue is the animal I'm thinking of is a mammal, right? So if the animal you guessed was a bird, then you know it's false, right? So my information I'm providing is it's kind of like taking a sample, right? It's not quite the same thing, but that's the analogy here. So when I provide you a piece of information, I'm giving you a clue. That's like taking a sample from the population. And sometimes that sample can prove a claim completely false, right? It can prove the null hypothesis false. I shouldn't say claim, but we're talking about the null hypothesis, right? If it's extreme enough, the assumption's bad, we can say that appears to be a false statement. Just like when I say my animal's a mammal, and if your animal that you were thinking of was a bird, it proves your guess false, right? It's unequivocal. However, if you were thinking of a mammal, like let's say you were thinking of a dog, okay, your guess could still be right, but you don't know that it's right. You don't know if the animal I'm thinking of is a dog. So it didn't prove your guess wrong. Your guess isn't necessarily false, but it doesn't mean it's true either, right? It falls into that in-between space. Your guess isn't necessarily false. It hasn't been falsified yet, but it hasn't been proven true yet either. And so that's what happens here. Now, the animal I was thinking of was a giraffe. I try to think of something a little bit more exotic that most people probably wouldn't think of. So a giraffe is a mammal, but, and if I said, oh, this animal has a long neck or something, of course, that probably eliminates almost all other guesses. But so I say mammal because there's a lot of other animals that are mammals that you could have guessed that would still be wrong, even though my clue didn't prove your guess wrong yet. So your guess might have still, if you guessed dog, that was still a wrong guess, but you didn't have the evidence to prove it false yet. But you didn't have the evidence to prove it true either, right? So that's what's happening here. Either we reject the null hypothesis because the evidence is so strong that the assumption is bad, that we can go ahead and make that conclusion that this is a false statement. Again, we're never 100% certain statistics, right? Alpha kind of determines how certain we are about that. Or we say the evidence was not strong enough to prove this false, but it doesn't necessarily mean it's true either. We just couldn't show it was false with the information we had. All right, that's the initial conclusion that you draw, and that's sort of the output of the machine, right? So think of our pencil factory. We input the null and the alternative hypothesis. It runs through this machinery, which is what's nice about this is once you do these problems a couple of times, the machine, you get used to it. It's just, it follows the same exact steps every single time, right? Alpha, left tail, right tail, two tail test statistic, critical value, p-value, then draw your conclusion. And those steps will be the same every single time for every problem. The details will be different, but the machinery works the same way every time. And then the output is reject or fail to reject the null hypothesis. That's what the machine spits out. Now we have to take that result, reject or fail to reject the null hypothesis, and then we have to state a conclusion about the claim itself. So we want to address the claim in the original problem. And so we'll talk about how to do that based on whether we reject or fail to reject. Excuse me, I just had lunch. Based on whether we reject or fail to reject, what do we conclude about the claim itself? Right. And so that is the process of hypothesis testing. Okay, let's talk about this first step of writing the claim in symbolic form. So here are some of the symbols you might use to write the claim in a mathematical way. So if the claim is about a proportion, a population proportion, you should represent that part of the claim with the letter P. If the claim is about a population mean, you should represent that part of the claim with a mu. Now I don't know, so this could change, but currently I'm kind of skipping the section about testing claims about the standard deviation. But in 8.1, it does, there are maybe some problems where you're just writing the claim in symbolic form. You're not really doing the hypothesis testing, and it might be about a standard deviation. So if that comes up, use sigma to represent the population standard deviation. It could say, for example, the population mean is equal to 5. It could say the population mean is greater than 5, and so, or less than 5. So I didn't put equals to on here because I think that one's kind of obvious, but you'll use some of those symbols in your claim as well. Equals to, less than, greater than. And sometimes they'll even say things like test a claim that the proportion is at least 50%. Now remember, at least, even though there's the word least in there, means that much or more. Or you have to be at least this tall to ride this ride means you have to be that tall or taller. And so at least is actually a greater than or equal to. It actually can just equal that number. At most would be a less than or equal to. And sometimes they'll have even trickier things in there, like test the claim that the majority of people feel this way about this candidate or something. Majority means greater than 50%. So it doesn't literally spell that out, but that's what majority would entail. So, all right. So that's the first step, is writing the claim. We're going to do an example in just a second. But once you have the claim, from there you can set up your null and your alternative hypothesis. Now the null hypothesis is often represented as H sub 0. Null is kind of, I don't know how to say this. I want to say the null result, but like null result usually means you get a 0 or nothing happened or whatever. So null and 0 are kind of associated with each other. So null hypothesis would be H sub 0. And the alternative hypothesis in this textbook is represented as H sub 1. I'm sorry, that's kind of hard to see, but it's a 1. Some other textbooks represent the alternative hypothesis as H sub A. So you'll see the letter A there for alternative, which makes sense. But this textbook uses a 1 because it's the next one after 0, right? I don't know, just unimaginative, but effective. All right, now to construct your hypotheses. My background is not statistics, so I could be speaking out of line here. But the current fashion is to write the null hypothesis with always an equals to. No matter what the claim is, no matter what else is going on, the null hypothesis is always the mean equals whatever, or the proportion equals whatever. But that's not how it used to be done. And I feel like something is lost by doing that. And I understand, I can understand the rationale, because there is a point in this process where it helps to just have the null hypothesis as just an equals to. but I think it hurts more in other ways. That's just my opinion. I could be wrong about it. So my approach to this change has been to, I have to go with it because like my stat lab has adopted this change. So I have to teach you the way to get the right answer on the homework. But the initial setup, I still do the same way that was done before. And then I say we simplify it to just equals to afterwards. And so to initially set up the null and the alternative hypothesis, these are the things that have to be satisfied. The claim has to become one of the hypotheses. The claim either needs to become the null hypothesis or it needs to become the alternative hypothesis. And you might think, oh, okay, I have a choice. You don't have a choice. The next two requirements will force it to go to one place or the other. The null hypothesis must contain equality. Now, that could mean that it's just equals to. Could be, equals to would be equality. And those are really squiggly lines. Sorry about that. It could also be less than or equal to, because that contains an equality. Or it could be greater than or equal to. So the null hypothesis has to be one of these symbols initially. And then once we set it up like this, then we simplify it to just equals to. But to start out, it could be less than or equal to or greater than or equal to. So that's the null hypothesis. It has to have equality in some form or another. The alternative hypothesis must be the exact opposite of the null hypothesis. So they have to be opposites of each other, which means the alternative hypothesis will not have equality. Because anytime you're taking the opposite of any of these, the equals to part won't be there, because the opposite of equals to is for it to not be equal to, right? So the opposite of less than or equal to is just greater than, no equals to. The opposite of greater than or equal to is less than. The opposite of equals to is not equals to, right? So the alternative hypothesis, being the opposite of the null, would have to be a statement without any equals to at all. And that's how, those rules will determine where the claim goes. So basically, if the claim has equality, it becomes the null hypothesis. If the claim does not have equality, then it cannot be the null hypothesis. It has to become the alternative hypothesis. And so that's how you'll kind of set this up, is you'll start with your claim, and then either put the claim as the null or the alternative. If there's equals to in the claim, put it as the null. If there's no equals to in the claim, put it as the alternative. And then the one that's still blank has to be the opposite of the one that's filled in. So you just put the opposite statement for the other one, and that becomes your null and your alternative hypothesis. All right, so let's practice setting up the claim and the hypotheses. So that's what these examples are for. So part A, 20% of adults smoke. Now they go on to give some further information, but for stating the claim and for setting up the hypotheses, we don't need the sample data. All right, we just need this statement here. This is the claim that's being made. 20% of adults smoke. That's the claim. We want to write that in mathematical form, in symbolic form. So this is kind of how I often will set this up. I'll write out the word claim, colon, and then I'll put the mathematical form of that statement. Now this is a percent. So if it's a percent or a fraction, or I don't know, maybe decimal is kind of a dangerous thing to say, but if it's a proportion or a percent or a fraction, then the claim is about a population proportion. And so we use P to represent that. And it's saying 20% of adults smoke. Exactly 20. Not less than 20%, not greater than 20%, exactly 20%. Now, when we write this in symbolic form, we convert the percent to decimal form. So the claim here is that the population proportion is equal to 0.20. Right. So from there, we are going to write our null hypothesis and our alternative hypothesis. We'll follow those rules we just talked about. The claim has to be one of these statements. It either becomes the null or it becomes the alternative. The null has to have equality. Well, our claim has equality, so that means the claim has to become the null hypothesis. If there's an equals to in the claim, it has to be the null hypothesis. I mean, if you tried to make it the alternative, let's say you put it over here by accident, the opposite of equals to would be not equals to, and so this violates the second rule. The null has to have equality. So if the claim has equality, it has to be the null, because if you tried to make it the alternative, you'd violate rule number 2. The null has to have equality in it. All right, so let's undo all that we just did there. Okay, so if the claim has equality, it becomes the null hypothesis. That's the simplest way to put it. And then the alternative has to be the opposite of the null. So the opposite of equals to we just talked about is not equals to. And so this would be the null hypothesis. Sorry, it's supposed to be a 0 there. And this would be the alternative hypothesis. All right, so that's for part A. Part B, the mean pulse rate, excuse me, in beats per minute of adult females is 76 or lower, right? So here the claim is that the mean, so we represent that with a mu, is 76 or lower. So lower would be less than, but it could also equal 76. So it's going to be less than or equal to 76. And so, and I'm sorry, maybe these examples weren't chosen in the best way because, again, we're definitely eventually, but before we get to the end of chapter 8, you're going to see every possible combination of things that can happen, hopefully, in my videos. So, but what I was saying is, unfortunately, the claim, again, contains equality, so the claim becomes the null hypothesis. So again, this doesn't always happen. Sometimes, about half the time, the claim becomes the alternative hypothesis. But for these two examples, in both cases, the claim has equality, so the claim becomes the null hypothesis. Then the opposite of less than or equal to is greater than. And so the alternative would have to be that mu is greater than 76. And I didn't really talk much about the alternative. You might say, why is the alternative here? Because then we're going to assume the null is true. We're going to either reject or fail to reject the null. So it seems like, why do we need the alternative hypothesis if all we refer to is the null hypothesis? So I'm sorry I didn't talk more about it. The alternative hypothesis is what must be true if we know that the null hypothesis is false, right? So if we can prove, prove is, statistically prove, which means there's a certain, margin of error. We might be 99% confident that it's not true, but we never are 100% confident. But if our conclusion, let's just state that, if our conclusion is to reject the null hypothesis, then that would also mean that we are accepting the alternative as true. Because if our conclusion is that this statement is false, that the mean is actually not less than or equal to 76, then what must be true in that case is that the mean is more than 76. So the alternative is there as what would have to be true in the case where the null hypothesis is considered false. Okay, let's take a look at the next topic. The test statistic is a value used in making a decision about the null hypothesis and is found by converting the sample statistic to a score with the assumption that the null hypothesis is true. All right, so to calculate the test statistic, we'll be given a formula, and we're going to take into account the sample data that we have, along with the null hypothesis, assuming that the null hypothesis is true. And then the value that we get as our test statistic will be used to judge that assumption. So again, if we get a ridiculous number for the test statistic, then we made a ridiculous assumption, which means the null hypothesis is probably not true. If we get a reasonable value for the test statistic, then it seems like we might have made a reasonable assumption, so we can't say that the null hypothesis is false, right? So that's kind of the two conclusions we might come to. The formula will be different if we're testing a claim about a proportion versus if we're testing a claim about a mean. And not only will the formula be different, we'll be using two different distributions just like we did in chapter 7. So if we're testing a claim about a proportion, we use the normal distribution, and our test statistic will be a z-score. If we're testing a claim about the mean, we're going to use the t-distribution, and our test statistic will be a t-score. So here's a chart with the various formulas, which I wouldn't bother writing these down just yet. We're going to see them again in 8.2 and 8.3 in the next videos, so I maybe wouldn't bother writing these down. And this third one here, we're probably not even going to address. I kind of criticized this in chapter 7. This is a case where you're trying to find something out about the population mean, and somehow you know the population standard deviation, which I was a little uncertain I was a little bit uncertain about in chapter 7. I don't know what I was thinking. Whether, like how common that might be. because I don't know, I kind of started to doubt myself because we were doing problems on it. I'm like, well, maybe it is more common than I think. But then in chapter 8, the notes I'm seeing that I'm using to kind of put these lessons together admit, like, that's pretty uncommon to not know the population mean, but to somehow know the population standard deviation. So with chapter 8, I'm just going to kind of skip that topic. So this is what we're going to be doing in 8.2, claims about proportions. We'll, be using that test statistic in 8.2. And then in 8.3, we're just going to do this one where we don't know the population standard deviation, in which case we're going to use the t-distribution, and this becomes our test statistic in that case. And like I said, currently, this would be 8.4, but I'm currently not going to cover this section, at least at this time. Maybe in the future I'll go back and kind of fill that information in. Now, the distribution here is a totally different distribution, and it's quite a bit different than the normal and the t-distribution have a lot of similarities. This is called the chi-square distribution, and it's completely different from these two. And so that's what makes it worth covering, is that it introduces another kind of distribution of data for you to become familiar with. However, hopefully we'll be seeing this later with a different topic. All right. So for the following, find the test statistic. So we'll go back to those formulas. I'll write them down again here, and maybe you'll get a better view of them. I know they're kind of hard to see on the previous screen. 20% of adults smoke. A recent Gallup survey of 1,100, not 100, I said that, I taught this face-to-face like a couple days ago, and I did the same thing. A recent Gallup survey of 1,016 randomly selected adults showed that 21% of respondents smoke, right? So this information is from our sample. This is the sample size. 21% would be the population proportion. No, sorry, I'm saying the wrong thing. This would be the sample proportion, which is going to be 0.21 when we convert it to decimal form. Now remember, the null hypothesis that we just did a moment ago on this situation was that p was equal to 0.20, and we're going to need that information as well to calculate the test statistic. So we don't have any evidence for this, but we are going to assume, for the sake of argument, that the null hypothesis is true. We're going to say, let's assume that p actually does equal 0.20. That's the population proportion. Our sample proportion was 21%, 0.21. Our sample size was n. And what we'll also need is q. And so if p is equal to 0.20, and whenever you see a p and a q, p is, I'm saying the wrong, well, it would be true, actually, what I was about to say. I don't know why I was doing so good earlier. Now I'm just like jumbling up my words. Q is always 1 minus p, right? Q hat is 1 minus p hat. You're going to see this in chapter 9, but Q bar is 1 minus P bar. So anytime you see P and Q in a problem, Q is always 1 minus that P for whatever particular thing you're looking at. So Q is going to be 1 minus 0.20, which gives me a value of Q equal to 0.8. Let's try that again. 0.80. All right. So with that information, we can calculate the test statistic. So the formula is this. We have the sample proportion, p hat, minus p, divided by the square root. Let's try that again. I'm going to try the fraction bar again too. Square root of p times q over n. Right. And I just actually want to go back, because these formulas start to get pretty complicated, and sometimes the details get a little bit foggy for me. So let me go back and double check just to make sure. Yeah, so that's the formula. We got it right. So plug the numbers in that we have just identified. So p hat is 0.21 minus p, which we're assuming to be 0.20, divided by the square root, I'm sorry, I'm doing a horrible job of writing now, square root of p, which is 0.20, times q, which we identified, calculated as 0.80, divided by n, which is 1,116. All right, so I'm sorry about not the fraction bar, the square root symbol there. All right, so that's plugging the numbers into the formula, and then we take that formula and plug it into our calculator. I should go down a little bit further here with that too. Okay, because that whole thing's in the square. The 1,016 is also inside that square root. I just want to make sure that's clear. All right, so when I go to type this into my calculator, Many students like to just type it all in at once, which is fine. But this numerator, while on paper, you don't need parentheses around this. When you type it into your calculator, you might. So you probably want to put parentheses around that. So parentheses 0.21 minus 0.20, close the parentheses, divided by the square root of 0.2 times 0.8 divided by 1016 in the square root. And I end up getting 0.7, I don't know how many decimal places to go, 797. I'll just go 3 decimal places. All right. My stat lab should tell you how many decimal places to carry that calculation. Now, we've worked with z-scores throughout this course. And if you remember way back when we introduced z-scores back in chapter 3, we talked about usual versus unusual values. And the rule of thumb is that if the z-score is bigger than 2, it means the data value is an unusual data value. So this z-score is not bigger than 2. Also, if it's less than -2, it's an unusual value, right? And this is not less than -2. It's right in between -2 and 2, which means it's just an ordinary result. There's nothing extreme about it. It's just a normal outcome from a normal situation, you know? And I hesitate to use the word normal because I'm not talking about the normal distribution here. I just mean it's ordinary. It's unremarkable, right? It's just a common value. It's a common result. And because of that, it seems like this assumption is not a bad assumption. Because in comparison to that assumption, this sample is about what you would expect, right? These are the kind of numbers we expect to get in the normal course of things, right? When we get z-scores that are bigger than 2, that's when things are unusual and we're getting results that we wouldn't expect, you know, given the assumption. But if this assumption is true, this is the kind of result that you would expect to get from your sample, and the z-score bears that out, right? It's a very ordinary, typical type of z-score. So the assumption doesn't seem to be bad. But again, we don't want to say it's true necessarily. It's just this data would not prove this false, right? This is not extreme enough to make me doubt this assumption because I'm getting a very common value given this assumption, right? So in the light of this assumption, this sample seems to be quite ordinary. So I wouldn't doubt the assumption. Again, that's getting ahead of myself here because that's kind of getting to the conclusion part of the whole process, but just kind of get you thinking in those terms, right? Normal z-score means probably an okay assumption, which means the assumption doesn't seem to be false. So we probably are not going to reject the null hypothesis in this case because ordinary outcome means ordinary null hypothesis, which means it's, you know, unlikely to be false. Again, I probably shouldn't say it like that. We wouldn't want to say it's true necessarily, but the evidence definitely doesn't make this seem like it's false. Okay, I'm going to stop talking about it. All right, let's look at part B. Now this time we're talking about a mean, so we want to use this formula, t equals x bar minus mu over s divided by the square root of n. So we have to track down all these numbers. So for a random sample of adult females, the mean pulse rate is 77.5. That's the sample mean. The standard deviation was 3 from the sample. So that's the sample standard deviation. N is 150. And the mu, because we need a number for this, will come from the null hypothesis. So go back to the original problem where we first saw this problem. The null hypothesis was that mu was less than or equal to 76. All right. Now I forgot to do this actually, so we need to go back. So that's traditionally what we would leave the null hypothesis as. But here's where it comes in handy simplifying in the way that they want us to simplify. So and I'm sorry I forgot to say this back here. In my stat lab, you won't find this as the correct answer. It may not even be an option. So on my stat lab, the null and alternative hypothesis are multiple choice options, but usually there's like 6 or 8 of them. So you actually have quite a lot to look at. One of them might be this one, but it'll count it wrong. So what you want to do is simplify the null hypothesis. So while it should start out like this, we are going to simplify it to just equals to for the purposes of what we want to plug into our formulas later. And I should have said that back here when I did this problem. So this is actually the correct answer that you want to select on my stat lab. So take the null hypothesis, reduce it to just equals 2, because again, we're going to assume the null is true. And so basically we are assuming this. We're assuming that the mean could be any number less than 76 or equal to 76, right? So that's our assumption. It could be less than or equal to 76. However, when it comes to this point where I have to actually pick a number to plug into this formula, I need to make a choice. So the best choice to make is worst case scenario. The largest that the mean could be is 76. That's as big of a value as you would expect given the assumption that we're going to make, right? So if we assume this is true, we're going to assume that this is true, but we have to pick a number from our assumption to plug in for mu. Worst case scenario is that the mean could be 76. That's the largest number you would possibly have. If anything, it might be smaller than that. So you want to consider the worst case scenario for testing this claim. And the worst case scenario here is the mean might be as big as 76. So I don't know if that makes sense. But if you simplified it, then you just go with the simplification, right? So the null simplifies to this. That gives us the number that we actually want to plug in for mu. All right, so we're going to plug in 76 here. So let's go ahead and plug these numbers in. The sample mean is 77.5 minus the population mean we're assuming is 76, even though we also assumed it could be anything less than that. The worst case scenario is it might be as large as 76. The sample standard deviation is 3, and the sample size is 150. Now, when you go to plug this into your calculator, you have to use parentheses again. So on paper, it's fine to write like this, but in your calculator, when it's all going to end up on one line, we have to make sure we're careful with the order of operation. So parentheses are needed to show this is the numerator, this is the denominator. So we have to actually put parentheses around the numerator and the denominator this time for the calculator to do the calculation correctly. So 77.5 minus 76, parentheses around that. And I'm sorry, I put S again. That's weird. I'll change that in just a second. I didn't even notice it. Divided by 3 over the square root of 150. So square root 150. And close the parentheses on the square root, and then close the parentheses on the denominator, because we're putting the denominator in parentheses as well. All right, so let me erase that real quick. Well, it's a big eraser. Let's see. Oh, I can make it smaller here. Okay, that's better. All right, and that should have been 3. I apologize for that. Okay, and I end up getting 6.124 as the t-score for this test statistic. Now, it's a different distribution. You know, t distribution is a little bit different than the normal distribution, but the score would be between -2 and 2. For a t distribution, it might fluctuate a little bit from that, but it should stay pretty close. So around -2 to +2 would be considered a normal, again, I keep using the word normal, would be considered a usual ordinary t value, a t-score. So anything beyond 2, maybe 2.5. So maybe it really depends on the degree of freedom, right? So worst case scenario would be like -2.5 to +2.5 would be considered usual. And that's for a really low degree of freedom, right? Anything beyond that would be considered unusual for sure. So 6 just is clearly beyond what we would consider to be ordinary or typical or usual. And so that makes me doubt this assumption, because how do I want to say this? It looks unusual because of the assumption that we've made, right? If you assume the mean is 76, then 77.5 as a sample mean is unusual. So there's 2 possibilities here. Maybe we do have an unusual sample, but if it's unusual, that should be rare, right? A t-score of 6 should only happen like 0.1% of the time, right? It's a very unusual outcome. It's rare. It doesn't happen very often. And that might be what happened to us. Maybe we just happened to get this really bizarre, rare sample that produced a really uncommon mean. And so we got a t-score that reflected that. But what's more likely is this is an ordinary sample that you typically get from the population, and our assumption is actually bad, right? So the chance that this is just a really rare mean is very, very, very small. So the other option is obviously much more probable, right? Which is we made a bad assumption. that the population mean actually is not 76. It's actually higher than that, which means that this is actually more of an ordinary sample. It just looks unusual because of our bad assumption, right? So in this case, if you get an extreme value, it's because you made a bad assumption. That's the explanation we're going to go with, rather than we just got this really uncommon sample that gave us a really uncommon value. I think it's a typical common sample, and we just got a bad assumption that made it look like it was uncommon when it really wasn't. All right. So the next phase is to determine the value of alpha and whether you will be doing a two-tailed, left-tailed, or right-tailed test. So I like to usually give a reasoning for why it ends up happening like this. So I guess let me start off by saying, in comparison to chapter 7, when you're doing a confidence interval, you take your value of alpha and you always divide it in two. And half of the alpha goes in the left tail, half goes into the right tail. So for confidence intervals, it's always a two-tail situation. But that is not the case for hypothesis testing. So in some problems, we are only concerned about the left tail of the distribution. And in that case, all of the alpha goes into the left tail. You don't divide it in half. You place all of it into just the left tail. Other cases, we're concerned with just the right tail, in which case all of the alpha goes into the right tail. So other times we are concerned with both tails, and in those cases we do divide the alpha by 2 and put half of it in the left tail, half of it in the right tail, just like in chapter 7. So any of those are possible. So you have to kind of, consider the situation to decide what you should be doing with alpha in order to get the right critical value or critical values. In the case of a two-tailed test, you'll have 2 critical values. Now, the driving factor here is which tail we should be concerned about in regards to the assumption that the null hypothesis is true. In what direction would we start to doubt the assumption? So let's consider just briefly, and again, this is not anything you need to know for the homework, but I just want you to understand the reasoning behind how we decide whether it's left tail, right tail, or two-tail. Right, so go back to this claim here, the one that we had, that the pulse rates were less than or equal to 76, right? And that ended up being our null hypothesis. Right. Now, again, when you simplify this to just equals to, you lose the ability to reason about what we're about to talk about, which is why I don't like simplifying it to just equals to, because then you lose the reason for why you're doing a left tail, right tail, or two-tail test. It's based on this before you simplify this to just equals to. You are assuming that the mean could be less than or equal to 76. Now, for the purposes of plugging a number in for mu into our formulas, we're going to assume it's equal to 76, but our assumption is that it might be less than that as well. So if you think about the normal distribution, and let's say, given this assumption, we're assuming the mean could equal 76, so let's put 76 here in the middle. Because that, again, that'd be the biggest value that we would assume it's equal to. But let's say we take a sample, and our mean in the sample comes out equal to 71. Well, that's pretty far away from 76, which makes 76 look like a bad assumption, really. But it doesn't go against this assumption, because I assumed it could be less than 76. So 71 actually supports this assumption that the mean is less than or equal to 76. Right? So if I'm getting samples over here in the left tail, even if they're extreme relative to 76, they actually are consistent with the assumption that I'm making from my null hypothesis. So it's fine if it's over here. If it's 71, fine. I assumed it was less than 76. So 71 actually supports that assumption. If I get 65, well, yeah, that's really far away from 76, but that's fine because I assumed it could be less than 76, so 65 actually fits in that assumption as well, right? It's consistent with that assumption. The only time I'm going to start to doubt this assumption is if it creeps in the other direction, right? If I get like 77, right? Well, I thought it would be less than 76, right? I assumed it would be less than 76. So if it's climbing away in the other direction, greater than 76, that's when this assumption starts to look doubtful. And if I get a sample mean of like 79, well then this assumption doesn't look valid at all, because this sample mean is greater than 76, whereas I was assuming the mean would be less than 76. So it's this direction that makes me start to doubt this assumption. It's the right tail that I'm concerned about. So this situation ends up being a right tail test. So whatever our value for alpha is, we put all of it into the right tail because that's the area of concern. That's the area where I would start to doubt the assumption that the null hypothesis is true. If it goes into the left tail, I don't care. It actually fits my assumption, and so it's not a concern for me. It only becomes a concern if it heads towards the right tail. So this is a right tail situation. Now, how are you, now that's the reasoning behind it, but there's a very simple way of determining that, which is, again, I feel like the redesign of the approach is because there's a simple way of telling whether it's left tail, right tail, or two tail, so the reasoning doesn't matter anymore. But that, I don't know. I'm not okay with that. The reasons matter. That's what I care about. Right? But but for you, you might not really care about that, and that's fine. You don't need to know what I just talked about. What you do need to know is you can determine this by looking at not the null hypothesis, but there's a shortcut way of determining this by looking at the alternative hypothesis. Right? And so the alternative in this case, remember, the opposite of less than or equal to is greater than. And greater than will always be a right tail test. Not only is it a shortcut, it's really perfect, right? Because greater than should make you think of going to the right? Bigger numbers get bigger to the right. So greater than is already associated with heading in the right direction. And so it's a right tail test. If the alternative is a less than, then it's a left tail test, which again is perfect because it just lines up, the directions just line up perfectly. And if it's not equals to, that's when it's a two tail test. All right, so I don't know if I have that written down on here somewhere. No, I don't. Okay, so let me go ahead and write that down on the screen for you. So it's all based, it's not even based on the alternative, but that's the shortcut. You can look at the alternative hypothesis to determine whether it's left tail, right tail, or two tail. Right. So if the alternative is not equals to, then it's a two tail test. In that case, you take the alpha, divide it by 2, half in the left tail, half in the right tail, and you'll have two critical values. If the alternative is a less than, it's a left tail test. In that case, all of your alpha goes in the left tail, and there's only one critical value, and it's in the left tail. If your alternative hypothesis is a greater than, like it was in this case, that will be a right tail test. But again, the reason it's a right tail test actually has to do with the null hypothesis and this assumption before you simplify this to just equals to, right? Because you're actually assuming that it could be less than 76 as well. So the left tail is not a concern. Anything in the left tail is consistent with the assumption. The only thing that isn't consistent with the assumption is if it goes to the right of 76. That's when it becomes inconsistent. Now again, if it's just a little bit to the right, you could chalk that up to variance. But if it's too far to the right, then the assumption appears to be flawed. And so again, how do we decide what's too far? Where do we draw that line? That's what the critical value is for. And that's what alpha is going to help us find. And that's what we're about to do here in just a minute. So, but this is the shortcut for determining if it's left tail, right tail, or two tail. And I'm going to use this shortcut from here on out, but I wanted to take the time to explain the reasoning behind the deciding what tail test we're doing. All right, so look at the next topic. So critical values. So again, third step. So I guess I kind of went out of order, didn't I? So the third step was to find alpha and left tail, right tail, or two tail test. Fourth step was test statistic, which we did before. So I did that before we did and again, the order for those two doesn't really matter. You could do those in either order. It's fine. Then the fifth step is critical value and p-value. So let's talk about those. The critical values, or value, I guess let's just keep it singular because that's the grammar that I have there. The critical value is the value of the given distribution that corresponds to an area in the left, right, or both tails that, it corresponds to the significance level alpha. So maybe my wording's a little bit out of order there. But the critical value is the either z-score or t-score that corresponds to an area of alpha, either in the left tail, right tail, or in both tails, depending on whether we're doing left, right, or two-tail test. Right? The critical value is the threshold value for what we should consider as a reasonable test statistic, given that our assumption is true. If a test statistic goes beyond the critical value, further into the left or right tail, meaning it's more extreme than the critical value, we must doubt the truth of the assumption which yielded such a result, which means we would doubt the null hypothesis, which means we reject the null hypothesis. All right. So the critical value is where we're drawing the line. It's how we determine what's ordinary, what's usual, what's typical versus what's too extreme to continue to accept the assumption that we were making. All right. Okay. So let's find critical values. For these examples, let's assume the significance level is 0.05. So again, to find the critical value, it matters whether it's a left tail, right tail, or two-tail test. And determining that, we need the alternative hypothesis. So we have to kind of go back to the hypotheses that we set up for these. So, and we really just need the alternative. That's our shortcut, right? So remember the alternative hypothesis, if you have to go back, rewind the video, you can see what we came up with for this, was that P does not equal 0.20. That was the alternative hypothesis. The not equals 2 tells me that this is a two-tail test, which means I want to take alpha, which is 0.05, but I want to divide that in 2 because I have to cover both tails, the left tail and the right tail. So I'll take the alpha I was provided, divide it in half to cover both the left tail and the right tail. Right? And so I end up getting a value of 0.025. Sorry about that. Okay, let's try that again. 0.025. So it's a normal distribution because it's about a proportion. So this is the normal distribution here. We're going to find a z-score as our critical value. Half the alpha goes into the left tail, so that's 0.025. Half the alpha goes into the right tail, so that's 0.025 as well. Oh, sorry about that. It's not writing very well for me today. All right, there we go. And so there's going to be two critical values this time, one in the left tail and one in the right tail. To find that critical value, we have the area. We want to find the z-score that corresponds to that area. So just like in chapter 7, we're going to do inverse norm. And I guess I'm going to do that up here. So we're going to do inverse norm. Whoops, skip the letter R. Inverse norm. And then area to the left is 0.025. And that's all you need. You don't need degree of freedom for normal distribution. And so this is going to give me, I'll use my calculator. I should memorize that. You know, I had these memorized at one point, but then I'm not teaching the classes often. And so I feel like now I don't really remember them as well as I used to. So this is going to give me negative 1.96. I'm just going to round to 2 decimal places. It's pretty common. And that's the critical value in the left tail. All right, so let me kind of draw an arrow up here. But we also want to find the critical value in the right tail, right? I want to find what this number is. But because of the symmetry, and for z-scores, 0 is right in the middle. So if this value is negative 1.96, then for the right tail with the same area in the tail, the value will be the same except it'll be positive. So the right tail will be positive 1.96. So take advantage of that symmetry. And so part A actually has two critical values. So that's where we draw the line, right? And so anything more extreme than these z-scores, any test statistic that is more extreme than these z-scores will cause us to reject the null hypothesis. But if it's in between the two z-scores, we fail to reject. So this is already kind of a messy drawing, and I'm out of, I guess I could use green. So if our test statistic is in the left tail or right tail past these critical values, we would reject the null hypothesis. I'm just leaving out letters left and right here. Reject the null hypothesis. Now I'm kind of skipping ahead. Again, it's hard for me not to. It's all connected. So when I get one piece of information, I automatically connect it to something else. It's hard just to look at them separately like we're supposed to in section 8.1. Same thing over here in this green area. If our test statistic, that gets hard to say over and over and over, is between these two numbers, if it's between negative 1.96 and positive 1.96, we fail to reject. So just keep that in mind as we move to the next phase of the problem. Right, we fail to reject the null hypothesis if it's in between. All right, let's take a look at part B. All right, so this time again, alpha is I don't know why I'm doing colon there, is 0.05, just like the direction said. But this time it will not be a two-tailed test. We just talked about this in the last screen. The alternative hypothesis here is that the mean is greater than 76, which means this will be a right tail test. So we do not divide the alpha in two. I'm going to draw my distribution. This time it's a t-distribution, but again, it looks really similar to the normal distribution. All of this alpha goes into the right tail. We don't divide it in two because we don't have to cover the left tail this time. We only want to cover the right tail. So all of the alpha goes just into the right tail, all 0.05 of it. And this time we're just going to have one critical value. Now to find this critical value, we have to use inverse t. All right, inverse t. Technically, we should do the area to the left, but here's another little shortcut, because that's an extra calculation you have to do. So again, the normal distribution is symmetric, zero's in the middle. So what you can do is just use this as your area, even though that's the area to the right. And what you're actually going to find is the value in the left tail, but because of the symmetry, you know the number will be the same except positive for the right tail. So I'm going to do inverse t. I think we use this shortcut. It was a little bit of a different situation in chapter 7, but same idea. We just use the area to the left, but if our value is supposed to be in the right tail, it's the same number, just drop the negative sign. That's what we're going to do here. The other thing we need is the degree of freedom. Right? The degree of freedom is 1 minus n. That's going to be 150. I forgot to copy that information over here. So something I realized when I taught this in class is that they give us some information about the sample, but they didn't tell us the sample size or the standard deviation. So I added it in earlier, but I forgot to put it here. So if you remember, the sample size that I added in earlier was 150. So it's going to be 150 minus 1, which gives me a degree of freedom of 149. And so that's what I want to put here. So we do inverse t, 0.05 for the area, 149 for the degree of freedom, and that's going to give me my critical value. Inverse t, 0.05, comma 149. And let's see what we end up getting. So again, my calculator tells me negative 1.66 if I go 2 decimal places. But because this is, I'm stuttering now. Because this is in the right tail, I drop the negative sign. It needs to be positive. So I know the number's good, but then I have to decide what the sign should be. If it's in the left tail, keep it negative. If it's in the right tail, it should be positive. Right? So positive 1.66. That's the critical value, which is often labeled as t sub alpha, not divided by 2 this time because we didn't divide it by 2. So you just do t sub alpha as the critical value. And that's the only one. And again, that's where we draw the line. If our test statistic crosses this line further into the right tail, we will have to reject the assumption. We're going to have to reject the null hypothesis. But if it doesn't cross this line, if it stays anywhere to the left of it, even if it goes way extreme into the left tail, that's okay. We will fail to reject the null hypothesis in that case. So fail to reject the null hypothesis there. So keep that in mind when we get to that next phase and have to make that decision. All right, let's take a look at the next topic. Okay, so the other method of deciding whether you should reject or fail to reject the null hypothesis is to use p-values. The p-value is the probability of getting a value of the test statistic that is at least as extreme as the one representing the data value, assuming that the null hypothesis is true. Now with the p-value, what you're going to do is take your test statistic, find the area corresponding to that test statistic, and the direction you want to find the area in depends on whether it's a left tail, right tail, or a two-tail test. So if it's a left tail test, you want to find the area to the left of the test statistic. And I'm sorry, on the recording, this is my left, but it might look like I'm going to the right on the recording, so I'm sorry about that. For a right tail test, you want to find the area to the right of the test statistic. And that's regardless of where it's located. Now, normally, most well-formed problems, if the test statistic is closer to the left tail, then you want the area to the left. If it's closer to the right tail, you want the area to the right. That's generally how it works. But I have seen 1 or 2 problems where the test statistic is closer to the left tail, but it's actually a right tail test. So you still want to find the area to the right, even though it's going to be a gigantic area. So it's supposed to be the tail test that determines which way you go. Left tail, area to the left, right tail, area to the right for the p-value. For a two-tail test, that one, you always go to you want to find the area to the closest tail. So if the test statistic is closer to the left tail, find the area to the left. If it's closer to the right tail, find the area to the right. But then you double the area that you get. So this is the one detail a lot of students kind of mess up on, right? So the p-value is twice the area to the tail nearest the test statistic. The reason you're doubling the area, I said that kind of funny. The reason you are doubling the area to get the p-value in the case of a two-tail test is that makes up for the fact that you would have had to divide the alpha by 2. Right? So for a two-tail test, you normally divide the alpha in 2 to get the critical value in the left and the right tail. But the concept of the p-value is that you're not going to do anything with alpha. You just want to compare a number to alpha, whatever it happens to be. So instead of dividing the alpha by 2 to make the comparison, you double the value of the area you get from the test statistic to make the comparison. Right? So rather than dividing alpha by 2, you double this value from the test statistic, and that becomes your p-value. So, all right. So let's find the p-value for these test statistics here. So we have to go back and get the test statistic, which I don't remember at this point. I don't know if you can tell, but I've paused the recording multiple times, and I'm already at an hour for the recording, but I've been doing this for probably an hour and a half, 2 hours now, because I keep pausing it and doing something else and coming back. Okay. And so I don't remember what the test statistic was, and I'm afraid I won't even remember it through all these clicks. All right. So what, did I go back too far? I think I did. Okay. So the test statistic, let's do part B first since it's here on the screen. 6.124. I think I can remember that. 6.124. 6.124. Let's get back to p-value. So 6.124. I better hurry up and write it down before I forget. 6.124. All right, so that was the test statistic for part B. Oh, sorry about that. I did a bad job of putting that in a box. All right, we want to find the p-value for that test statistic. The other thing we have to know is, was it a left tail, right tail, or two-tail test? So remember, the alternative hypothesis was that mu was greater than 76, which means this is a right tail test, which means for the p-value, we want to find the area to the right of 6.124, which is the direction you would expect because this number is in the right tail, right? 0's in the middle. This is positive, so it's going to be to the right, 6.124. And we want to find the area to the right of that. We want to find the area in the right tail. I don't know if I'm saying this right. We want to find the area to the right of 6.124. That's probably the best way to say it. Now, to find this area, it's a t-distribution, remember. So we also need degree of freedom. Almost forgot about that, which is 149, right? To find that area, we're going to do something that we didn't have to do in Chapter 7. So this might be the first time we're doing this function. It's a t-distribution, so we don't want to use normal CDF. We want to use t-CDF. And my recollection is that some TI calculators didn't used to have this. Either they didn't have inverse t or they didn't have this one. I can't remember which one they were missing. So hopefully your calculator has this function, t-CDF. And it works just like normal CDF. You want the lower bound, which is 6.124. So for this shaded region, the lower bound is 6.124. The upper bound is infinity. And for that, I use 9999999 as a substitute. But then you don't need to put the mean or the standard deviation if it's a t-score. You don't need to state those other things, but you do need the degree of freedom. And so that would go third. So 149 is the degree of freedom. So we're going to do distribution, t-CDF, 6.124, comma, 9999999, bunch of nines, comma, 149. And I end up with a pretty small value. So I end up getting 3.8. You might say that doesn't seem small. It is. 3.867. I'm just going to go for significant figures because it's times 10 to the negative 9. Right? Not pretty small. It's really small. For some reason, I thought it said negative 4 at first. It's negative 9. It's 10,000 times smaller than what I thought it was originally, right? or about. I don't know if I did that calculation quite accurately in my head, but it's much, much smaller. Orders of magnitude smaller than to the -4. All right, so as an ordinary number, if I convert this from scientific notation back to like a regular number, there's 8 zeros here. So 0.000000000. That's 8 zeros. Then we hit the 3867. That is the p-value in this case. And that is a number that we compare to alpha to draw our conclusion. And I'll talk about how that works when we get to that phase of the process. All right, so there's p-value for part B. For part A, we have to go back and get the test statistic, which was a z-score. And I remember it was 0.7 something. It's not still on my calculator, unfortunately. So let's head back to that same page right here. And we will scroll up, and it is 0.797. That's not going to be too hard to remember. 0.797. All right, so that's the test statistic. Remember this one, the alternative hypothesis was p does not equal 0.20, so it was a two-tailed test, which means we want to find the area to the closest tail. All right, so let me make a little more room to draw a picture. So we're going to draw a picture of the normal distribution. Try to anyways. 0 is going to be in the middle. The test statistic is positive, so it'll be to the right of that 0, 0.797. And for a two-tail test, you find the area to the closest tail. So if you're closer to the right tail, find the area to the right. If you're closer to the left tail, just find the area to the left. So it could go either way for a two-tail test. So I want to find this area because it's a normal distribution this time. So when it's proportions, you're using the normal distribution. We want to use normal CDF. Lower bound is 0.797 for that area. The upper bound, it goes to the right forever, so infinity. Sorry, I put a comma, but that's it. Right? We don't need anything else. Let me just undo that comma. All right. Oh, let's try that one more time. Okay. Still a horrible looking parentheses, but all right. So we plug that into our calculator. Normal CDF. 0.797, comma, a bunch of nines for infinity. And that's it. And we get 0.2127. Right. Now I feel like I'm thinking about when I cover this in class, and I wonder if I forgot to do this. It's an easy thing to forget. Because it's a two-tail test, you have to double this area. I might have forgot to do it because that's such a large p-value. You'll get used to, once you see a few of these, you'll realize, usually p-values are like around 0.1, 0.05, somewhere in that area. Sometimes even lower than like the last one we did, 0.0000, right? 0.21 is a pretty large p-value already. So I might have forgot to do this last step, which is because it's a two-tail test, you have to double that area because we don't want to divide the alpha by 2 to make the comparison. We're going to double this area instead to make the comparison, right? And so that's going to give me, if I multiply that by 2, we're going to get 0.42, I'll go 4 significant digits. Oh, that was weird. Why did I do that? 0.4255. That looks like a completely new number to me, like I've never seen it before. So I'm almost sure I forgot to do that in my face-to-face class. So that was a mistake on my part. All right, so that's the p-value for part A. So you have to make sure you double it if it's a two-tail test. All right, let's go on to the next phase of the problem. We're going to skip this one. Sorry, I meant to delete all these out. I guess I forgot to do that one. All right, let's talk about this. Okay, so how do we draw our initial conclusion? You can either use the critical value and compare that to the test statistic to decide whether you should reject or fail to reject, or you can use the p-value comparing that to alpha to make that decision. So for the critical value, I'm just going to kind of map this out here. So if it's a left tail test, for a left tail test, your critical value will be in the left tail. So let's say your critical value is right here. If your test statistic ends up further to the left in the left tail, you will reject the null hypothesis. Let's try that again. Reject the null hypothesis. If it's anywhere to the right of that critical value, you will fail to reject the null hypothesis. All right. Sorry for the lull there. Okay. If it's a right tail test, and we kind of mapped this out already, but I just want to have a place where it kind of fits all together, every possible scenario, right? The distribution looks like this. It's kind of a horrible drawing, but I'm just going to leave it. Then you'll have a critical value in the right tail. If it's a right tail test, your critical value will be over here in the right tail. If your test statistic ends up further into the right tail past that critical value, that's the case where you would reject. What is wrong with how I'm writing now for some reason? Okay, reject the null hypothesis. If it's anywhere to the left of that critical value, you would fail to reject. All right, let's see. Okay, fail to reject the null hypothesis. All right, and then the last possible scenario is if it's a two-tail test. So it would look like this. In the case of a two-tail test, well, let me try that one more time. Oh, that was still pretty bad. Maybe a little bit slower this time. Okay, that was okay. You'll have two critical values. And if your test statistic crosses either of them further into either tail, you are going to reject the null hypothesis. But if it's in between, you would fail to reject. All right, so that's how you use the critical value to draw your conclusion, your initial conclusion. If you want to use the p-value, and this is why they've made the move to the p-value, and I'll admit this is much more elegant, much simpler to state and to make a decision. If the p-value is greater than alpha, you fail to reject the null hypothesis. If the p-value is less than or equal to alpha, you reject the null hypothesis. So that's how you would make the decision using the p-value. All right, so let's practice doing that. Let's see. Am I missing something here? Let's see. I don't know. I feel like I might have skipped this problem in the other class, and I feel like the hypotheses were blank. I might have forgot to actually type those in. For the XOR gender selection baby, or let's see, what am I saying? For the XOR baby gender test, the test had a test statistic of this, a p-value of this. The hypotheses were, I don't have the hypotheses, but we can still make a decision even though we don't see what the hypotheses are. So let's just go ahead and do this, because what ultimately you make the decision based on comparing the test statistic, which we're given, to the critical value, which we can calculate using the significance level of 0.05. Or comparing the p-value to the alpha, which again, we can make that comparison. So we can decide whether to reject or fail to reject. What we don't know by missing this information is whether this was a claim about a proportion or about a mean. But I'm guessing it's proportion since we're talking about gender tests. So it's like what proportion were boys, what proportion were girls. So let's assume it's a proportion, and so it's a normal distribution for finding the critical value, right? So let's use the critical value. So I'm sorry, it's a poorly formed problem. I left out some detail here, but I think we'll be okay. And so the significance level is 0.05. Actually, no, we can't do this. Well, we have the p-value though, but we can't find the critical value unless we know it's a left tail, right tail, or two-tail test. So why don't we just skip this example? I apologize that we're missing that important detail. And let's go back to our previous examples where we do have all the information we need. So let's go back to the A and B, the proportion of people that smoke and the pulse rates for women, right? Those were our previous two examples. We have all the information we need to make decisions there. So let's just go back to that. And I've kind of already alluded to what these would be. So for part A, our p-value was 0.4255. To draw a conclusion based on the p-value, you compare that to alpha. Now, alpha, for these problems, we've been letting it be 0.05. Right? So alpha is 0.05. Our p-value is this. So compare those together, p-value and alpha. P-value is 0.4255. Alpha is 0.05. So the p-value is greater than alpha in this case. If it's greater than, we fail to reject the null hypothesis. So that's how you make your initial conclusion there. Fail to reject the null hypothesis. If you want to use the critical value method, then we compare the critical value, which we found previously. The critical value, it was a two-tailed test, so actually there was two critical values, and they were at 1.96 and negative 1.96. Those are our critical values here. And our test statistic is 0.797, right? And so that would be in between these two, right? So again, 0 is right here. 0.797 is going to be a little bit past 0, like right here. It's in between my critical values, so again, we would conclude to fail to reject. You should get the same conclusion either way you go. Whether you're comparing critical value to test statistic or p-value to alpha, your initial conclusion should be the same either way. All right, but that's how you would use the critical value, and this is how you would do the p-value comparison. All right, let's do the same thing for part B. Critical value, let's do critical value first this time. So this time there was only one critical value. It was in the right tail. Do I still have it on my calculator? I don't actually, so let's go back. I already forgot what it was. Sorry about that. So let's go back and find it. Critical value was 1.66. Wasn't very big of a number, right? So 1.66, which would be right here. Wait, did I go far enough? No, I didn't. Yeah, I did. Okay, right here. This is where we want to be. So our critical value, where we're drawing the line, is at 1.66. Our test statistic is past that, right? It's a right tail test. This is the only critical value. If our test statistic goes past that critical value further into the right tail, which it does, because it's in this area here, we are going to reject the null hypothesis this time. That's how you would determine that using the critical value, comparing that to the test statistic. For the p-value method, the p-value, compare that to alpha. Again, the p-value is this. It's that 0.8 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 3, 8, 6, 7. Alpha is 0.05. In this case, the p-value is less than alpha, so that means we should reject the null hypothesis. So again, same conclusion from that. So that's how you make your initial conclusion using either the p-value or the critical value. Right. Okay, we skipped that one. And we skipped this one because it was just a poorly formed, not poorly formed, just missing an important piece of information. And again, I apologize for that. And I don't want to record this whole video over again because of that one piece of missing information. So I'm just going to leave it, as embarrassing as that is for me. All right. Now, the last step is to state the final conclusion. And we want to make this statement in plain language. We don't want it to be technical, mathematically written. We want to think of it as, when somebody makes the claim, they're using plain language. It's not technical or mathematical. We want to make the conclusion in the same language so that a layman could understand the claim and the conclusion. So because again, if we leave it the way we have it, if we say, okay, so we reject the null hypothesis, that's what happened. And you tell that to somebody who's never taken statistics, that's just going to go over their head. They're going to have no idea what you mean by that. They won't know what to think, right? So we want to word the conclusion, first of all, in language that anybody can understand, even if they've never taken a statistics class, but also in reference to the claim, not to the null hypothesis, right? We're trying to state a conclusion about the claim that was stated in the original problem. So I would recommend using this flowchart and sticking to the scripts that they provide, because while we want to use plain language, we do have to be careful the wording that we use. So sometimes I've had students on the test where they don't really have the script handy and they just kind of freestyle it, and they think they're saying the same thing as what the script says, but it's not quite the same. Use the flowchart, stick with the script. That's the safest thing to do. Does the original claim contain the condition of equality? I feel like I said that funny. So either yes or no. Now, why that's important is this determines whether the claim became the null or if it became the alternative, because that makes a difference. If the claim became the null hypothesis, and then we decide to reject the null hypothesis, we are rejecting the claim because the claim was the null hypothesis. So rejecting the null becomes rejecting the claim. However, if the claim became the alternative hypothesis and we end up rejecting the null, that actually means we prove the alternative. We accept the alternative as true, which means in that case, we would say the claim is true. So it matters whether the claim becomes the null or the alternative. If we reject the null and the claim was the null, then we're saying that the claim is false. If the claim was the alternative, we're going to say that the claim is true, right? And so that's what this is getting at. Does the original claim contain the condition of equality? If yes, that means it became the null hypothesis. If no, it became the alternative hypothesis. All right. Do you reject the null hypothesis? If yes, this is the conclusion you should draw about the original claim. As I just mentioned, this path, the claim becomes the null hypothesis. If we reject the null, we are rejecting the claim. And notice that's what the wording here says. There is sufficient evidence to warrant rejection of the claim that, and then you fill in the details of what the claim actually said with no mathematical symbols. It's completely verbal, right? If we fail to reject, that means we were unable to show that the null hypothesis is false, which means we were unable to show that the original claim was false. But that doesn't mean it's true necessarily either, right? So there is sufficient evidence to warrant rejection. Sorry, I skipped the most important word in that sentence. There is not sufficient evidence to warrant rejection of the claim. Doesn't mean the claim is true, but there wasn't sufficient evidence to show that it was false. That's the script there. If the original claim does not contain equality, that means the claim became the alternative hypothesis. In that case, if we reject the null hypothesis, that means we are accepting the alternative hypothesis as true, which means we would be accepting the claim as true. And that's what this wording says. The sample data support the claim that blank. You fill in the details. If we do not reject the null hypothesis, that means we couldn't show that null hypothesis was false, which means we couldn't show that the alternative was true. And that's what this wording says. And the alternative being the claim, right? There is not sufficient evidence to support the claim that blank. So these are the four possible outcomes for the final conclusion regarding the claim. All right. So, well, here we have the claim, which maybe would have been helpful earlier. So with that one problem, but I don't know if, even though it's the XORT method again, this might be different details here. And so we're skipping all the other. So again, we're trying to look at things in isolation. So this example is just about stating the final claim. We don't want to have to go through the rest of the process for the hypothesis testing. We're going to be doing that in the next section, where we have to put it all together into one problem. So here the XORT method is effective. That's the claim. The XORT method is effective in increasing the probability that a baby girl will be born. Right? That means the claim. So what we have to actually think about this before we decide what the conclusion should be. Right? The claim, if it's effective, that means the proportion of girls that are born will be greater than 50%. Right? Because if it's effective, it should be increasing the number of girls that are born, because that's the gender that they're selecting for. And if it's actually effective, then you should be having more of that gender. So again, this one's kind of a tricky one because the claim is not very literal. You have to infer from the wording that this is what they mean by it. Which means that the null hypothesis and the alternative hypothesis would be thus. The claim has to be one of these. It doesn't have equality, so the claim has to become the alternative hypothesis. Right. Well, I'm sorry, I don't know why it keeps doing those extra little marks there when I'm writing. Okay, the null has to be the opposite of this, right? So the null is going to be the opposite of greater than, which will be less than or equal to. So you see that when you take the opposite of the alternative, for the null hypothesis, the equality part should show up there because the null always has to have equality, right? So there's the null, there's the alternative hypothesis based on this claim that we were given. Right, now that's important. Now what they end up saying is that given the test statistic and a significance level of 0.05, the initial conclusion was to fail to reject the null hypothesis. So we failed to reject the null. So what should my final conclusion be then? Well, I guess we didn't have to set this up, right? If we follow the flow chart, it kind of tells us what to say. The original claim does not contain equality, so therefore it became the alternative hypothesis, right? So following this flow chart, this decision tree, does the original claim contain equality? No. So we go this way. Right? And so notice here it says original claim does not contain equality and becomes the alternative. That's exactly what happened in this example. Do we reject the null hypothesis? Well, we're told we don't have the details of it, but I'm like, oh, what did I do there? I went the wrong direction. But we are told that we fail to reject. So no, we do not reject the null hypothesis. Oh, I forgot there's another topic after this. I thought we were almost done. So no, so we should use this script here. There is not sufficient evidence to support the claim that blank. All right, so I'm going to go ahead. I'm going to pause it so you don't have to sit there because it takes me forever to write out this sentence. So I'm going to pause the recording, write out the conclusion, and then I'll resume it so you can see what it should look like. Okay, so I found a way to type it out instead of me having to write it because it would also probably be hard to read if I was trying to write it. There is not sufficient sample evidence to support the claim that the XORT method is effective in increasing the probability that a baby girl will be born. So you make it a complete sentence using only words, incorporating the claim in there. All right, let's take a look at the last topic here. A type 1 error is the mistake of rejecting the null hypothesis when it is actually true. Alpha is used to represent the probability of a type 1 error. Now it's a mistake, but it's not your fault if this mistake is made. Right? You follow the number, you follow the process appropriately, you make the conclusions, I'm saying this kind of funny, you make the conclusion that the numbers tell you to make, but the conclusion was wrong anyways. So remember, when we are drawing our conclusion to, and when we're making our decision whether to reject the null hypothesis or not, there's really two possible explanations. One is that we made a bad assumption, and that's rejecting the null hypothesis. The other possibility is that we just have a rare sample, and that will happen some percent of the time. So while we will choose to reject the null hypothesis because that's the more probable explanation for why the numbers look the way they do, there is still that small chance that maybe the null hypothesis actually isn't false, and we are rejecting the null hypothesis when it's actually true. And we just happen to actually have a rare sample. And that's why it looked rare, because it actually was rare. It wasn't because we made a bad assumption. And so that's a type 1 error. A type 2 error is a mistake of failing to reject the null hypothesis when it is actually false. So again, that's another mistake we could possibly make, right? So beta is used to represent the probability of a type 2 error. And there is a way to calculate that, but it's not something you're going to be asked to do. Right, so these are basically false positives, false negatives. That's kind of what type 1 and type 2 errors are. All right, so here's all the possibilities of what can happen when you're either rejecting or failing to reject the null hypothesis. So one possibility is the null hypothesis is actually true, but because of the numbers you got, you decide to reject the null hypothesis even though it actually was true. And of course, that's a mistake, right? The process made a mistake in judgment. That's a type 1 error. The other possibility is that the null hypothesis is actually false, and then when you do the hypothesis testing, you decide to reject the null hypothesis because of the numbers you have, and that's actually a correct decision. It was false and you rejected it. So that's a correct decision. Another possibility is the null hypothesis is actually true, and you fail to reject the null hypothesis, which is the right decision. You didn't reject it, you didn't claim it was false, and it was actually true, so that's consistent, right? But another possibility is the null hypothesis is actually false, but you failed to reject it, even though it actually should have been rejected. That's a type 2 error, right? So those are type 1 and type 2 errors. So on the homework, you'll have a problem that's like this. Identify the type 1 error and the type 2 error that corresponds to the given hypothesis. So the proportion of college students who consume alcohol is greater than 70%, 0.7. So that's the claim. From that, we can construct our null and our alternative hypothesis. And then we can talk about what it would look like if we made a type 1 error or a type 2 error in that situation. All right, so first we need to write out the claim. All right. So the claim here is that P is greater than 0.7, which means for the hypotheses, since there's no equality here, we can't put that claim as the null, so it will have to become the alternative hypothesis. The null hypothesis will be the opposite of that. The opposite of greater than is less than or equal to. Right. Now for the purposes of my stat lab, they're going to ask you to simplify that, and so the alternative hypothesis becomes p equals 0.7. Right. So that's what you end up using as the null hypothesis, excuse me. Did I say alternative a minute ago? I might have said the wrong thing. So that's what you use as the null hypothesis. The alternative will still stay p is greater than 0.7. Now, if we happen to make a type 1 error, so I'm going to actually, and I've never really used this before, but I really found that handy last time, typing, when we have a big sentence, just typing it out instead of trying to write it. So what is a type 1 error going to look like? So a type 1 error occurs when p actually is less than or equal to 70%. So p is actually, and I shouldn't use capital P here, the population proportion is actually less than or equal to 0.7, but we reject the null hypothesis. So maybe I could even word it better like this. P is, let's say it like this. Let's put that in parentheses. The null hypothesis is actually true, well, I can't even spell, actually true, which means p is actually less than or equal to 0.7, but we reject the null hypothesis anyways, even though it's actually true. Asserting that p is not less than or equal to 0.7. All right. So that's what happens with a type 1 error. That's what it wants you to describe. So in this hypothesis testing, we're not going to actually go through the whole thing, but just given the hypotheses that we have, if we were to end up making a type 1 error, what would that look like? It would be the case where the null hypothesis is actually true, but we end up deciding to reject the null hypothesis because of the numbers that we had to work with. And so we would end up asserting that the null hypothesis is false, that it is not less than or equal to 0.7, when in fact it actually is less than or equal to 0.7. That's what it would look like if we make a type 1 error, right? So a type 2 error, what does that look like? So type 2 error, okay, let me expand this out a little bit here. So in this case, the null hypothesis is actually false. So p is not actually less than or equal to 0.7, but we fail to reject it. We fail to catch that it is false. The null hypothesis, excuse me, the null hypothesis. I can't spell hypothesis. All right. So we do not recognize that it is false. All right. So that's what a type 2 error would look like. Right? The null hypothesis actually, in reality, is a false statement, but we fail to reject it anyways, even though we should have. Right? So that's what a type 2 error would look like. So that's what they're asking you to do on these problems. Now, what kind of bothers students about this is like, well, which one is it? Is the null hypothesis actually true? Is it actually false? We don't know. Oh, I can't believe I spelled actually wrong, and I didn't even catch it this time. Sorry about that. We don't know, right? We're just saying hypothetically. If we happen to make a type 1 error, hypothetically, what would that mean? It would mean that the null hypothesis actually was true, but we rejected it as false. And hypothetically speaking, if we made a type 2 error, what would that mean? It means that hypothetically speaking, the null hypothesis is false, but we failed to reject it, even though it was actually false. All right, so that concludes the video on section 8.1. I will see you in the next video for section 8.